that make sense? Okay. Now, the most explanation you'll see on internet or textbook is called Bernoulli's principle. I didn't have enough time to talk about it before, but now I have some time. So let's talk about Bernoulli's principle. Bernoulli's principle is applying energy conservation to liquid. So it comes from this equation. For a system, no matter solid, liquid, gas, or whatever, the work done by external force, external non-conserving force, will end up changing the total energy of the system, which includes the kinetic energy of the center of mass, the internal energy, and the external potential energy of the entire system. That's a part of your homework last night. So, how do you map it into fluid? So, if there is no external non-conservative work done on the fluid, the sum of its energies will be a constant. Now, when you look at static fluid, you learn that if you go to a higher place in the water, the pressure difference will be rho g delta y with a minus sign, right? If you go higher, the pressure will increase or decrease. Good. The deeper, the higher the pressure. So if you go to shallow water, the pressure should increase. That's why there is a minus sign here. When your y position increases, pressure should decrease. Now, if I move this term to the other side, I get the change of pressure plus the change or plus rho density times g times the change of height is 0. To make it more clear of what I'm doing, I'm going to change this expression into the change of total energy of the system is 0. Now, can you see these two looks kind of similar? The change of these three add up to 0, and the change of these two add up to 0. One term is easy to recognize, is rho g delta y. When you are doing your homework, you learn that so this is not going to be in tomorrow's homework, but I will make a homework for this principle and come like that. It's going to be explain why this works, or explain why you should use contact effect, not Bernoulli's principle. That's going to be homework. So, you learn in your homework that if you increase the height of a particle with mass m by delta y, the change of potential energy will be the mass times g times delta y. Okay? You did that in your homework, right? The higher the particle is, the bigger the potential energy. So if you increase the height, you increase the potential energy. Now, when I'm looking at not particle, but a small part of water, let's say I'm looking at a small part of water, then I can say the total mass of the water is m. So I can choose a small part of water, so the y position is basically the y position of the center of mass. And the external potential energy will be the change of potential energy of the center of mass with mass m, which is the total mass of the entire drop of water. Okay? So this term will be the change of external potential energy of the water inside the cup. Okay? Now, there's still some difference between this term and rho g delta y. This is density. This is mass. So what should I do? I just divide the change of energy with the volume of the blood. Then I get the mass divided by volume, and this is what that term means. This rho g delta y is actually the change of energy density, and that energy is the external potential energy of the water. So this term corresponds to the external potential energy of the water in your cup. Now, if this is energy density, then this term should also be an energy density because I add them together. The dimension must make sense. You can use dimensional analysis to look at pressure. Pressure is force divided by area. And you can say it is force times length divided by area times length. What is an area times length?
Volume.
It will give you a volume, yes. Now, how do you do work to change energy? Is work force times change of time or force times change of distance? So time will give you impulse. If you push something for 2 seconds, that will change the momentum of the object. How do you change energy? What is work?
Force times distance.
Good. It's force times distance, or the dot product between force and displacement. Anyway, this is force times distance. So the dimension is the same as work, which is the same as energy. So you see, indeed, pressure is an energy density. So you look at these 3 terms. External potential energy is already taken, is rho g delta y. So you are left with 2 choices. One is the kinetic energy, and one is the internal energy. Now, is the water moving? Down here the water is not moving. Up here the water is not moving. It's steady fluid. So when I look at down here and up here, there's no change in kinetic energy. The kinetic energy is 0 both down here and up here. So what does pressure correspond to?
Internal energy.
It's actually internal energy. Pressure is actually the internal energy of the water. And the reason that the pressure will increase when you go deeper is actually due to energy conservation. When you go deeper, the potential energy of the water decreased, so the internal energy of the water increased, which is the pressure of the water. Okay? So far so good? Now, how do you add kinetic energy? You just look at the situation in which the water is flowing. when water is flowing, let's look at this example. If you were here last Thursday, you kind of seen the setup. I didn't prepare the setup today, but it's fine. So you can have water flowing inside a tube. So when the water is flowing, the velocity should change when you pass through a narrow tube because the tube is narrow. In order to pass the same amount of water through the tube for each given time, the velocity of the water should change when they pass through this tube. Should the velocity of water increase or decrease when you pass through this tube? It should increase, good. The velocity should increase so that it can pass through the same amount of water with just a smaller tube. So this shape of the tube will force the water to change its velocity. So this is the case which the water has velocity, and we just need to add kinetic energy to our equation. Because we are looking at kinetic energy, but our term is energy density. We should also look at energy density for kinetic energy. So that will give us kinetic energy per volume, which is 1/2 mv squared per volume. Kinetic energy is 1/2 mv squared. You need to memorize that. And if you divide it by volume, you will see that you are dividing the total mass of that part of water with its volume. What will you get by n divided by v?
Density.
Density, good. So you get 1/2 rho v squared instead of 1/2 mv squared. And I'm going to just write it as the change of these three things is 0. This is Bernoulli's equation. Do you know how to spell Bernoulli?